Today we're going to look at logarithms, and we're going to, our lesson goals for today are going to be that we're going to be able to understand what the logarithm function does and how it can be used to determine an unknown exponent. And we're also going to look at the logarithm laws for simplifying more complex logarithms. So the logarithm function is essentially the inverse of an exponent. It allows us to very simply and very easily determine the exponent when it is unknown. And previously we've had to find the same base and solving exponential equations, but this way we can rework an exponential equation to use the logarithm function to very easily solve it. The logarithm function is available on your calculator as the log button. So the logarithm function is a reworking of the exponential function, as I said. So essentially, if I've got an exponential of the form a to the power of x is equal to y, the logarithm function, we say log to the base a, so the logarithm function applying it to the base a of y is going to be equal to x, is equal to the exponent. So the exponent here is equal to the logarithm function to the base a. So the base for the exponent that we have here, the base for the exponential equation, the base for the exponent there is a. The base for the logarithm is also a. This is called the base. The value we get by multiplying ax times is going to be equal to y. So the logarithm function is the inverse of that and allows us to find the exponent very easily. So for example, if I've got 2 to the power of 4, I know 2 to the power of 4 is equal to 16. The log to the base 2 of 16 is equal to 4. So you can see where the reworking has occurred. The 16 is now what we're using inside the function. The 2 remains the base, and then the exponent is then the solution to this equation, or it's the same on both sides of this equation. So 2 to the power of 4 is equal to 16, and log to the base 2, 16, is equal to 4. So let's have a look at some examples now, and remembering this definition of what a logarithm is, that it's a reworking of exponent. We can have a look at how that applies in a few examples here. Hopefully that'll connect the ideas a little bit better for you. So for 1a here, we've got log to the base 2 of 8 is, and we've got to evaluate that. We've got to find out what log to the base 2 of 8 equals. And to figure this one out, what we need to do is we need to think, okay, well, what exponent would to the base with a base of 2 would yield 8? So we know that 2 to the power of 3 is the same as 8. So it means x equals 3, or it means that log to the base 2 of 8 equals 3. So if we look at b now, we've got log to the base 3 of 1/9. So log to the base 3 of 1/9. That's what we're trying to find. We're trying to find what that equals. And so we need to think about, well, what exponent to a base of 3 would yield 1/9? We know that 1/9 is 1/3 squared. And we know from our index laws that that's 3 to the power of -2. So that means that x in this equation is equal to -2. So that means that log to the base 3 of 1/9 is equal to -2. For 1c here, we've got log to the base 10 of 0.001. Now this is going to be the same as log of 10 to the 1/1000th, which is equal to log to the base 10 of 1/10 cubed, which is log to the base 10 of 10 to the -3. So we're being asked what exponent, so if the exponent is unknown, would we get 1 over 1,000 or 1/1000th? And we know that that's the same as 10 to the negative 3. So that means that x will be equal to negative 3. An interesting point to make when we're looking at log to the base 10, we're looking always at relating it to the base 10 and powers of 10. And we see this occur a lot of the time in things like scientific notation. It's very handy to be able to have things to a base of 10 with a raised power, either to a negative power or a positive power, because it allows us to just shift the decimal point. So we can very easily tell when we've got a log to the base 10 what the answer is going to be, because it's going to be how many decimal points it's been shifted. So if for this example here, I've shifted the decimal point 1, 2, 3 from 1. So because I've shifted it 3 places and it's gotten smaller, I've shifted it 3 places to the left to get 0.001, that means that the value for this logarithm is negative 3. If I was to find something, for the example, the log to the base 10 of 1,000 or 10,000, then here I've shifted the decimal point from 1, 1, 2, 3, 4 to the right. So the answer for this is 4, because 10 to the power of 4 is equal to 10,000. It's how many decimal points I've shifted it to the left. It's very, very handy to be able to quickly work that out and quickly think about that. Question 2 asks us to evaluate log to the base 10 of 0.5. Correct to 3 decimal places using the calculator. So when we're inputting this into our calculator, the log button on your calculator will almost always be just to the base 10. You need to use a special other log button to do it to anything other than base 10. But if you use the log button on your calculator, it should do it just simply straight to base 10. So log to the base 10 of 0.5, if we're putting that into the calculator, we're essentially asking the calculator, if I've got 10 to the power of x, what is going to yield 0.5? So the calculator does this very, very quickly, and it gives an answer that log to the base 10 of 0.5 is equal to negative 0.301. So that means if I put into the calculator, and you can check this, 10 to the power of negative 0.301, you should get 0.5 or thereabouts, because we've rounded it. So the calculator can be used to determine trickier logs very quickly. Question 3 says find the value of x in these equations. First we've got log for a, we've got log to the base 4 of 64 is equal to x. So we're being asked here, if I've got 4 to the power of x, that's going to equal 64. And in this case, 4 to the power of 3 is equal to 64. 4 times 4 is 16, times 4 again is equal to 64. So that means x in this case is equal to 3. For b, we've got log to the base 2 of x is equal to 6. And what we're being, if we were rearranging this, we'd be saying we've got the base 2, the exponent is 6, and that equals x. So that means x is just 2 to the power of 6, and 2 to the power of 6 is equal to 64. Because 2 times 2 is 4, and then if we do that 3 times, then we get 64. Now to looking at logarithm laws. The logarithm laws are derived from the index laws, and I'll show you a couple of those derivations very soon. But there are 3 laws, and they relate to the first 3, or there are 3 laws that we're discussing today, and each of these 3 laws matches up to the index laws. So the first law here is if I've got log to the base a of x plus log to the base a of y, then that's the same as log to the base a of x times y. And that relates to index law 1. Index law 2 very similar, and it relates, log law 2 is very similar, and except rather than subtraction, we've addition we've got subtraction, and rather than multiplication we've got division, and that relates to index law 2. Logarithm law 3 relates to index law 3. So if we're looking at deriving these now, I'll look at the first law and look at deriving it first. So let's say that x to the power of x is equal to a to the m, and y is equal to a to the n. Now, if I was to rework both of these two, they're equations, but I'm just sort of stating, I'm letting x equal a to the power of m and y equal a to the power of n. If I were to rework these using logs, then I can say that m is equal to log to the base a x, and for my y I get n is equal to log to the base a y. Now, x times y is a to the power of m times a to the power of n, because that's what I've said x is, and that's what I've said y is. So using index law 1, that's the same as a to the power of m plus n. Now if I rework this using the logarithm laws, I get that m plus n, which is the exponent here, is equal to log to the base a of xy. And I've said what m and n are before. I've stated that up here, what m and n are. So I can substitute those values of m and n down here. So I can get log to the base a x plus log to the base a y, and that is equal to log to the base a of x or y. So in going from this step to this step, all I've done is substituted in these values here into that equation. I'm not going to derive log law 2. It's very similar, and except it uses index law 2 rather than index law 1. So for the third law, however, slightly different. It uses index law 3. We know that x, I'm going to assign and say x is going to be equal to a to the power of m. So once again, m is equal to log to the base a of x. Now, if I've got x to the power of n, that's a to the power of m to the power of n. And we know from the third index law that this is the same as a to the power of m times n. So if I rework that using the log laws, I get that m times n is equal to log to the base a of x to the power of n. Now I can take my reworking here of my original definition of x is equal to a to the m and substitute in for m down here, and I get log to the base a of x times n, so it's just x times n, is equal to log to the base a x to the power of n. So this is n log a x is equal to log a x to the n. So you can see that's why we can say the exponent here in this log law can just go out the front and multiply by it because of that third index law. We can think about these other properties now as well of logarithms. So log to the base a of 1 is equal to 0. And we think about, for our reworking, if I've got a to the power of x equals 1, a to the power of 0 will always equal to 1. Anything to the power of 0 always equals 1. So that means if I've got log to the base a of 1, that means the exponent will always equal 0. So that's why it equals 0 here. Similarly, for the next one down here, if I've got, if I rework this, if I want to know what power is going to equal a, it's always going to be 1. Anything to the power of 1 it equals itself. So that's why in a reworking here, log to the base a of a is going to be equal to 1. If I've got log to the base a of 1 over x, then we can rework that using index law 3, or logarithm law 3 or logarithm law 2, in fact, to get the fact that we get negative log to the base a of x. So this is using a reworking using law 3, because negative 1 it then is multiplied out the front to get negative log a of x. We can also use log law 2. So if I've got use log law 2, that means this is equal to log to the base a of 1 is equal to, minus log to the base a of x using log law 2. Now log a to log to the base a of 1 is equal to 0. So we've got 0 minus log a x. So we end up with just negative log a x. So using index law, log law 2 or 3, we can get that if I've got log to the base a of 1 over anything, then it's just the same as the negative of log a to the value, the reciprocal of the value. So let's have a look at some examples now. Question 1a, we're looking at simplifying these following using the log laws. So we've got log to the base a of 4 plus log to the base a of 5. And we can use log law 1 to get that this is log to the base a of 4 times 5, which is log to the base a of 20. Looking at b, we get log a 22 minus log to the base a of 11. Now using log law 2, we can simplify this as log to the base a of 22 divided by 11, which is log to the base a of 2. 1c, 3 log to the base a of 2 is the same as log to the base a of 2 to the power of 3, which is log to the base a of 8. So that's the using log law 3. Question 2a, we're asked to simplify and evaluate these expressions. We've got log to the base 2 of 1. Now anything to, because if I've got here 2 to the power of anything, whatever it is equal to 1, x will always be 0. So that means that log to the base 2 of 1 is equal to 0. b, I've got log to the base 5 is going to equal 1, because anything to its own to the power of 1 is itself. For 2c, we've got log to the base 6 of 1 over 36. Now we can use here, we can simplify this to get that this is going to be 6 to the power of negative 2 here. Then this is going to be, we can use log law 3 to get negative 2 times log 6, and log to the base 6 of 6, it's itself, so that's going to be equal to 1. So we get negative 2 being the answer to 2c. Question 2d, we've got log to the base 2 6 minus log to the base 2 of 3. We can simplify using the second log law, and we get that this will be, because they're the same base, log to the base 2 is 6 over 3 using log law 2, and this is going to be simplified to log 2 to 2, and because it's the same base and the same value that we're taking the log of, then that's going to be equal to 1. So just to recap the learning goals for the lesson today, we looked at what a logarithm is, that it's a reworking of an exponential equation. We can use it to find the exponent, that logarithm function. And we also looked at the logarithm laws, where they come from, so how they're derived, and also how we can apply those log laws to simplify and evaluate equations or logarithms.